In the book, enter higher derivative. We already had this little bit of a higher derivative, and it has beautiful application. Physics starts that, right, first. So position, right? And then its derivative is a velocity, correct? And then the other day, we differentiate one more time, right? And Newton says this second derivative has important connection to the source of the forces and total force exerted into an object, something like this. So physicists wants that. So they started with st, differentiate, you arrive at derivative, right? Which is velocity. They differentiate it again and called acceleration. And these three quantities are very important. First derivative, right? At is the second derivative of the position. Does the term make sense? Vt is a first derivative of the position function. At is a second derivative of the position function. But at is a first derivative of the velocity function, right? Hope you see that connection. So we already understand that. That's a physics side. Here's a geometric side we're about to enter. It's wonderful. So remember what I'm doing in here? This is a point down there at 0, and we looked at the secant line, right? We computed the secant line, and if it is really, really close, that becomes a tangent line, right? So those are, when you play with the two points, you connect this, you get the straight line, so that's a linear function, right? What would be the generalization of this tangent line idea? 3 points, right? What if I stick to that x equals 0, not just 1 point, let me just throw one more point the other side like that. So I have 3 points. So if you try to connect the 3 points, do you always get a line? No, right? If I put just 3 points there, like this, like that, you can't draw a line. So what would be the next level of a function that might connect those 3 points? Any guess? 2 points obviously defines a line, right? What about 3 points? Okay, let me show you. Here's 3 points. Oh, here's a going beyond that. Let me explain. Here's the 3 points. I connected them. If there was this function I could discover that passed through these 3 points, which is not line, right? What's your guess? Parabola. It looks like a parabola, and it is a fact that if you write down 3 points, which is not line up perfectly, there's always a parabola, always a quadratic function that passes through the 3 points. Wonderful. All right. So what did we do after that? Once we have 2 points, we squeeze them down to 1 point, right? Let's do that. What if I squeeze that down to closer to 0? Then there is this quadratic function, right? And even that down it even further, down it further. If you even squeeze it further with mathematics or something, it doesn't change anymore. It's just almost there. Just like tangent line, when you get to that, getting closer to human eyes, the secant line doesn't change anymore. It's just there, right? Now we're getting playing with the 3 points. Now we're getting new object, right? This quadratic function. Interesting, right? What should I call this one? Before that was like tangent line, right? What should I call that one? Tangent parabola, maybe, right? I made it up. There's no tangent parabola out there, but we're going to call this one tangent parabola. What is tangency good about it? If you go in there, maybe I'm going to zoom in. Now I zoom in. Zoom in like that. And if you really zoom in here, you don't see the difference. Wow, that orange curve is completely covered up with the blue one, right? So isn't that a good approximation? It looks like a good approximation. It fails right there and right there. But up until here, that quadratic function I came up with is a pretty good approximation of that. So they use that as an approximate idea. It does much better than tangent line. All right? So then they enter this idea of approximation, this idea coming from the tangent line. So you have to remember this word, approximation now. It's very, very important business in mathematics and science. You can't get exact answer. You have to approximate it. And how are you going to do that? Is a systematic way of doing that and is a glimpse toward to that, right? So here it's one formula you have to write it down. This approximation business goes straight to analysis where there's no graph, there's no position or anything. They just took out the sense and just played it within in the functional analogy. So write down analysis, It's just about function, not necessarily putting into y equals f of x in xy plane. And they're talking about some approximation business. This is called polynomial approximation. Linear function, parabola, quadratic function, those are called polynomials. Now we're looking at this first level linear function, and you write it down, this word linear approximation at C. We're going to use this term all the time. If I say linear approximation of at C, you should know what to write down and what to compute. So here's the answer, linear approximation. Left-hand side, your complicated formula, f of x. Might have sine in it, it might have log in it. Those things you cannot compute by hand, so you always rely on a calculator. Right-hand side, on the contrary, something you can actually compute. So let's look at the right-hand side, and someone tell me what that is. Oh, I know what that is. Yes, that's the right-hand side of a tangent line formula, right? So tangent line, if you look at the tangent line of the graph, if you zoom in just like before, it is pretty close, but it's not as good as that quadratic formula, right? So it is not as good as quadratic, but it's still a good approximation. So they put not equal symbol. What did they put? F of x is approximately equal. So this value for what kind of x? X not exactly c, but x is close to c, just around is a c plus, 1/10 and c minus 1/10. Just around those points, this right hand side is pretty close to f of x. All right? Fair enough? So what is the name of this one? Linear approximation. Don't just stop at linear approximation. Understand linear approximation at where? At C. You have to choose a point. This approximation is only valid small amount of interval around it. So you have one linear approximation for what same function and different linear approximation for that's exactly the same function. Okay? All right. I'm about to do this example for you, but I'm going to challenge you to go ahead and use your calculator, something like that, and fold it up. Do not look at the formula, but turn it into an exercise. See if you can reproduce it on your own. So is that exercise number 2? State the general formula of a linear approximation at C. It is not about this example. The general formula with F's and C's in it, right? The very, very general formula. That's your exercise. If possible, please hide it, with a calculator and see if you can reproduce it. It's probably in your note. All right, did it work? Tangent line, right? F of C, that's where the function starts. Around it, we replace it with this line, right? Not the complicated function. And I use this equal symbol, curiously, right? Before I use squiggly approximate symbol, right? So I'm going to name it here. I forgot to do that. I'm doing it at the same time. I'm going to call this L of x. You know where L come from, right? It's a linear approximation of f of x. So f of x is approximately equal to this linear approximation. We wrote it down. Fair enough? Okay. All right, this is your challenge now. What is a linear approximation of this function in here, f of x, 2 times sine x minus 3 times cosine x? Exercise 3. Is that 4? Okay, this was 3 then? Okay, exercise 4. That's right, I made it into two ones, right? So f of x is that. Compute Lx, linear approximation at where? C equals 0 is a better notation. Let me change that to C. And understand the difference between C and X here, right? X is a variable. C is kind of here, that something that we want to approximate this little piece, tiny piece around there. And those around those X coordinate is X. But this C here is a 0. This is the end of it. This is a remark. This is a remark, and up to here is the final answer. It's a remark. All right. My suggestion is go ahead and write this one down. Repeat it verbatim. Repeat this one. Exactly. Lx equals f of c plus f prime of c times x minus c. And begin to answer. What is my c? What is my f of c? What is my f prime of c? And replace it on except x. You should not touch x. X is the variable for the approximation, right? All right. Was that okay? Yes? Yes. Yeah, the 2 times x. I thought about it, but I did not write it. But it was okay. That is perfectly. Yeah. What is fun? It's fun to write it like this. Yes. No, I'd like to keep it in x minus c form. It's much more information is there than expanding it. Yeah. Right? Good? I don't know. At this point, no, but it could change tomorrow. All right. Any other question? All right. What's our next goal? That quadratic approximation, right? Quadratic approximation. So let me give you some idea. The linear, you can write it like this. Here's I don't know, some value b plus slope m x minus a. What is this one called? What's that? Tangent line, but there's no tangent line. It is always a pre-calculus thing. What is the name of this one? Formula? Point slope formula. Point slope. We started from there. So I'm going to call this one m1 in here. Anything that passed through a comma b with a slope m1, right? That line looks like that. So Next level is that, all right, anything that passed through that line at that point A comma B, but is something like this, part of a quadratic. What would be the most general formula? If you think about it a little bit, keeping this structure is having to be important. B is there, right? M1, whatever the coefficient is coming, is x minus a. That point right there, a comma b is still there. And then they have to throw in quadratic term. That quadratic term, just to be consistent with this one, they use x minus a. So that if you plug in x equals a, it still passes through b because these are all zeros, right? And then throw in some parameter here. Whatever that coefficient in front of that quadratic term, it must be defined. This is the idea. This should be the point slope, not no, point parabola formula, whatever, something like that, right? If this is a point slope formula, this should be like point parabola formula. How about that, right? Okay. Okay. So we want our quadratic approximation something like this. B times plus m1 x minus a plus m2 x minus a squared. This is what we wanted. Okay. So if it's going to look like that, the whatever that I showed you before with the 3 points get together, and this should be approximately equal to our original function f of x, correct? This is our idea. So how are we going to actually proceed with this idea of approximate? And you're going to learn this more sophisticated, more rigorous idea in Calculus 2 at the end of the Calculus 2. Here's some naive, but still interesting idea. If these two things are approximately equal around x equals a, or here, let me change the c here. So that's now it's going to be c. That's going to be f of c, where that point is passing through. Apologize. How about here? I want the derivative at that point should be the same. Don't you think that's a good thing to impose? If it is a good approximation, derivative of this guy, derivative of that guy should be the same. Doesn't it look like a reasonable idea? It's not a proof. It's an idea. If it is really good approximation, how about derivative of this one and here? This is the second derivative. I forgot to introduce the notation. The derivative one more time, they put this 2 dotted in there, 2 prime. So s of prime of t, that's the velocity there, right? And if you differentiate one more time to that one, they put this one more prime in there. It's an easy notation I forgot to introduce. That becomes acceleration. Does that make sense? Yeah, differentiating 2 times. So if I differentiate it 2 times, it must be the same derivative at that point in there. If it is approximate, that seems like a reasonable thing to put. All right? Fair enough? All right. So I'm going to calculate what happened if I impose it and what happened to this thing. Yes. Yeah. Something like that. Yeah. Very good guess. It's half of the time it's correct. Yeah. So you will see how this one. But that is a correct idea. So this is the idea, right? I'm not proving anything. Let's impose that idea. That's what happened. All right. So I'm going to play with the first condition and play with the second condition. Fair enough? All right. So this is a long explanation. At the end, I summarize it. All you have to do is just memorize that one, right? But here's a little bit of idea. Okay. So left-hand side, I'm going to just leave it there. Right-hand side is a new guy, right? New contender. So I'm going to differentiate q prime of x, right? This is a constant. X is the only variable, right? So it becomes a 0 according to the sum and difference rule. It's just like constant. There's no x in it, right? M is a constant multiple. And if you differentiate this one, it becomes just 1. Okay? And then this is a constant multiple, M2, we want to figure out. And if you differentiate this one, you have to expand it, right? Like this. Fair enough? And differentiate it. Can you differentiate that? This is supposed to be C, I apologize. I changed that to C. It's 2C, and it's a C squared. So derivative of x squared, 2x, right? 2c is a constant multiples. It multiplied, so you don't have to touch it. What about x? becomes 1. What about c squared? Becomes a 0. All right, that's q prime of x. And we want to compare that one as q prime of c. What happens at that c is the derivative is equal to the derivative of f prime of c. So what is q prime of c? Is a 0 is m1 plus m2. What happened if you plug in c here? This is simply 2x minus 2c, correct? What happened if you plug in c there? 2c minus 2c, right? So it's a 0. So you will be able to, all right, if this happens, q prime of c is that precisely that coefficient m1, and we want this thing to be f prime of c. We have a formula of this one, and we want to discover the right coefficient such that it has this property. And a conclusion, that m1 that we're looking for in here is precisely m prime of c. So if you just look at it here, we just discover the tangent line again, right? If you replace it f prime of c there. Good? So I'm going for the next one. Next one compares f q double prime of c and that one. So I'm going to go for here, q double prime of c. That means you just have to differentiate this one more time. So here's to be x first. Here's the q prime of x. I'm differentiating one more time. Is m1 a constant? It's constant. There's no x in it, right? So it's a 0. m2 is a constant multiple there, right? So you keep it there. What happened if you differentiate this one? Derivative of 2x? 2, right? How about 2c? That's a constant, right? So it's a negative 0. So it happened after you differentiated 2 times, x disappeared. Just simply left with a 2m2. That's it. But it has this m2 that we want to determine. But this should be, now if you plug in q double prime of c, that's this idea, should be equal that there's no x in it, so constant, so it's m2, and that should be equal to the second derivative value here, f double prime of c. So we want to figure out what this m2 should be. What is m2? Yet f double prime of c divided by 2. So going back, summarize it here. If there's ever quadratic function in that shape, which is approximately equal to f of x, such that its first derivative value at c, second derivative value at c, if they are equal, so that it looks like a good approximation, then m1 should be m prime of c, and m2 should be f double prime of c divided by 2. So that quadratic approximation now, how does it look like? It starts from f of c. Remember? What was m2 now? F prime of c, x minus c, right? What is m2? F double prime of c divided by 2, x minus c squared. This is the formula. What is this formula about? What is this one called? What kind of approximation? Quadratic approximation. All right? So if you just look at the first two terms, do you still see the linear approximation? Linear approximation is still there. When you enter quadratic approximation, all you have to do is just add this one more term there. That's a quadratic approximation. Okay? So we computed this one at whatever the point we see, and if you throw it in there, this quadratic function, if you sketch it, it's going to look just like this. Okay? I also have a better picture there, I think. This is a linear approximation we computed together, and this is a quadratic approximation that computed together. You can see that's much better there, right? So if you use that formula that we have computed there, all you have to do, the right-hand side is a relatively simple arithmetic. You know, the actual function has sine and cosine. You have to use a calculator to get the good values. All right? So we're going to continue with this quadratic